Okay, so up ahead, we're supposed to take a left up here. Oh, it looks like we're gonna be oh no, I meant right! Oh my god, I meant right! Oh, we're taking a turn for the west! We're gonna crash!
Oh, you're gonna have to jump!
Oh, I'm gonna have to jump! I'm gonna have to jump! Okay. Oh god. Be very careful, you need a parachute when you do this.
Don't try this at home.
Don't try. Oh no! I'm in free fall right now, so my acceleration due to gravity is negative 9.8 meters per second squared. Now, I've reached terminal velocity because I'm traveling at a constant velocity, which means there is zero acceleration. Now I can land safely on the ground, assuming I don't hit any bloody trees.
Your crew's still on the plane. The plane is about to crash, so we're gonna have to jump too. We're coming, Blair! We're coming!
Our helicopter has dropped us off in the midst of the Alaskan wilderness. We begin our journey now. Hello, I'm Blair Grills, and welcome to an episode of Man vs. Wild. Well, today it's actually Woman vs. Wild. In this special episode, we'll be in the midst of the Alaskan wilderness. My brother Bear is sick, so I'll be taking his place today, and despite the rumors, he does go on these expeditions by himself. He does not have help. However, today I will be having my crew members / my friends come along with me on this expedition in our journey through the Alaskan wilderness. Hopefully we'll make it out alive, and we'll show you what to do if you get stuck in situations like this. Okay, these are my crew members. First is camera woman Jane Buffalo.
Hello.
Wilderness expert Elizabeth Fisherman. And yeah, so we'll help you survive through these conditions.
We're gonna be doing physics as well, because it's a very important thing to learn for survival.
So true, James. So true.
Any one wrong step could put you in the bottom of this crevasse. Look, I found something. Seems like a giant lava rock. Knocked it over. Oh my goodness.
Let's try to scale the top.
Oh my goodness. Oh my goodness. Oh my goodness. We're in the middle on top of a glacier.
Any small slip could send us
Straight to the bottom.
straight to the bottom.
That would be us. This is us.
This is us if we fall. Dead.
Oh my goodness. This crevasse is way too deep. The only way to get across seems to either be scale our way down or jump.
Blair, look, we found a bridge to cross.
Oh! Whoa, but we have to scale the bottom to get there. How are we going to do it? Only do this as a last resort. The only way is to scale the bottom. Well, as we all know, mechanical energy can't be conserved because it's converted into other kinds of energy due to the air resistance and friction. Remember, friction is a non-conservative force. All this means is that the work done by or against the force in moving an object is dependent on the object's path. Okay, so as you can see here, I'm about to slide down a hill with a height of 20 meters and a distance of 35 meters. The angle of the hill is about 35 degrees, and the coefficient of friction for my snow pants, made from nylon, and on the snow is about 0.3. Also, since I'm on Earth, my acceleration is due to the gravity, and thus it is simply 9.8 meters per second squared. If I use the equation PE equals W plus KE, where W is mu mg cosine theta, then I'm able to calculate my velocity going down the hill. Remember, you must be careful when sliding down a massive hill like this, because your velocity could get too fast and you could get out of control. I ended up going 14.9 meters per second. It seems we found a snow bunny! I think we can trap it by making a makeshift trap out of these sticks.
We caught her.
It worked.
We caught her. Within the hour, the snow bunny was trapped and incapable of breathing for longer than 30 seconds.
We finally have our food for the day.
We're gonna cook her up and have some stew.
The only problem is we don't have any fire. I found my crew, and look at all the wood they've chopped. So let's take a look at them trying to chop this wood. Alright, well, since changing object momentum, you have to change your force over time. Remember, it's a vector quantity, so in order to get the maximum change in momentum, you need to have a maximum force over a large amount of time. So by Elizabeth over there, Lumberjack Elizabeth, trying to chop that wood, if she lifts it high in the air and then brings it back down, she's going to get the most change of momentum. Thus, this tree will split in half at her command. And so, she's just chopped all this wood, and it's just great. We're going to go build a fire now, so we'll check back in with you later. Building a campfire is a classic example of friction. The kinetic friction is the frictional force exerted on one surface by another when two of the surfaces rub against each other because one force of the object is moving. In this case, the stick would rub against the log to produce kinetic friction. The static friction is a kind of response force. It responds to the applied force. Here, the applied force is pressing down on the log with the stick. Usually static friction is greater than the kinetic friction because it's harder to make something move than it is to keep it moving. Friction is a non-conservative force. This means that the work done or against by the force is in a moving against the object is dependent on the object's path.
Speaking of the work done while building a campfire, okay, well, there are 3 requirements in order for work to be done. First, a force must be exerted. In this case, Blair is exerting a force on the stick as she rubs her hands together and presses down on the stick. Second, the object that the force is being applied to must move. The stick never has a displacement of 0 because it would be impossible to obtain a fire without rapid movement of the stick. Finally, a component of this force must be in the direction of the displacement. The force Blair is exerting goes down towards the stump. The direction of the displacement of the stick is down as well. Therefore, work is being done in this system.
Now that we've established that Blair has done work, it is important to remember that when work is done on a system, the energy of that system increases. So, by rapidly rubbing the stick between our hands onto the log, the energy of the system would increase, thus creating a fire. The phenomenon is known as the work energy theorem, where work equals a change in kinetic energy.
Oh, we have fire! My circadian rhythm is so off. Oh, I knew it was summer here in Alaska because it's been daylight all day. I mean, I know it's raining right now, but it is light out all the time, and my body clock is so out of whack, I have to force myself to sleep. It is terrible. I mean, I just don't even know what I'm going. Oh, ow! Oh, my arm! Ow! The change in the body's momentum is equal to the impulse exerted on the body. Impulse is simply force times the change in time. As we saw, I ran into the tree and rebounded. Although we are unsure as to what my initial and rebound velocities are, if you want to find the change in momentum, you would use the equation mass times rebound velocity minus mass times initial velocity. It is important to note that the initial velocity is negative because I'm going in the opposite direction than I am when I rebound.
I'm really hungry. I bet there's a lot of animals back for the summertime. Oh, look! There's berries in the tree. Ow, Jane!
Oh, man!
Ouch, that had to hurt. This is an example of an elastic collision, which involves the bouncing of objects off one another. In elastic collisions, both momentum and kinetic energy are conserved, as seen here, because both objects rebound in the opposite direction after the collision.
Hey, Blair, is that your friend Edward? He looks like he's hunting something.
It is. I wonder why he's out there. I mean, he's not even supposed to be out here right now, but he's one of the best people to find food. Let's watch him and maybe we can join him for dinner. Here, Edward engages in an inelastic collision with the deer because he collides with and sticks together with the deer. In an inelastic collision, momentum is conserved, but kinetic energy is not. As we can see here, Edward and the deer have different masses and different velocities right before the collision. Edward has more mass and is traveling at a faster velocity than the deer. Whenever one object has a bigger mass or greater velocity, the two objects will go in the direction of the bigger or the faster object is moving originally. So after the collision, both Edward and the deer move in the same direction that Edward was originally going. Edward, that was incredible. I didn't know you were going to be out here this month.
I don't have the strength to stay away from you anymore.
Oh, well, it looks like we found civilization. Thank you for stopping by on this special episode of Woman vs. Wild, a journey through the Alaskan wilderness. I'm Blair Grills.
And I'm Elizabeth Fisherman. Thanks for stopping by.
And I'm Jane Buffalo. You stay classy, Planet Earth.
Thanks for stopping by.
Stay classy.
Thanks for stopping by.
I'm Jane Buffalo.
Young hearts, I believe that we are not far from becoming who we truly are. Love is on its way. is getting darker. Love is on its way.